Hello, ready for this quick run through the homework. Thought I'd do it like this just for saving a bit of time. Number one, again, see how I've highlighted bits of the question. It's about ions, so I'm already thinking active transport, facilitated diffusion. I'm not going to be writing about osmosis or just simple diffusion. And in one of the flask F, there's no ATP, so I'm thinking, right, no active transport. So flask G is going to be doing active transport. Flask F is going to be doing facilitated diffusion. So that's what I'm thinking before I start. Ratio, sorry. What's it called? Tangent. There it is. Tangent. Yeah, I've drawn my tangent. You get a lot of leeway with this, but it should be following the line pretty much. So yeah, my change in the Y is 10. It's come down 10. It's gone across 40. I got 44 there. So yeah, my answer is 0.23. I don't need a minus because it says calculate the initial rate of uptake of sodium ions by this tissue. I know this is coming down, but this is measuring the concentration of sodium ions in the solution, so it would be going up in the cell proportionately. So yeah, 0.23. Doesn't say I have to round it to a number of decimal places, so I've just gone for 2. And then B, which is a hard one. Yeah, scientists concluded that the cells in flask G took up sodium ions by active transport. Oh, good, I was thinking that anyway. Explain how the information given supports this conclusion. So I have to compare G to F. I'm using all the information. So all I've put is that, yeah, it's faster in G than in F. Yeah, it was steeper than in G than in F. They're both using proteins to move stuff across, but yeah, G is faster. And then I just put, yeah, that's because it's told me that there's ATP, so there's a bit of comprehension here. G has ATP and F does not, and active transport needs ATP. And then I've also put, yeah, that in flask G it's dropped to 0, and that means in G the tissue is moving the sodium ions up the concentration gradient. Again, I'm going to again when you look at yours, have you answered this exact question, or have you talked about other things instead? A few people were describing the graph instead. And then on to C. Flask F, it leveled off after 20 minutes. Explain why. Well, again, I've kind of preempted it. Yeah, it's using facilitated diffusion. It's reached equilibrium. Yeah, no more is coming in. It's reached that equilibrium. And then number 2 is very similar. So they love asking this with oxygen, without oxygen scenario. So now it's plant cells in a solution, different concentrations of calcium ions, right? So it's active transport or facilitated diffusion again. She measured the rate, right? I'm going to highlight rate because I'm a nightmare for getting this wrong. I know it. She measured the rate, right? So this is a rate graph of calcium ions by plant cells, and the graph below, well, I've shifted it to the right instead, but hopefully you coped with that. So then I look at my graph. I've got a concentration of calcium ions in the solution. So I've done a series of experiments at different concentrations, and I've measured the rate of uptake. With oxygen, it kind of increased straight away, and it's starting to level out. Oh yeah, it's starting to get to like a limiting factor graph. It's reaching a maximum rate for some reason. When it's not got oxygen, right, well, it can only do facilitated diffusion. And yeah, it's doing nothing at lower concentrations, so there mustn't be the concentration gradient for it to work. And then from 0.1, it's starting to come into the cells. And I've kind of shown that as like a little visual thing down here. It says, what can you conclude from the graph about the processes? Right, so I need to talk about the processes, so active transport and facilitated diffusion, involved in the uptake of calcium ions. Yeah, I'm just reinforcing that by these plant cells. Use evidence from the graph to support your answer. And I'm just going to, I wouldn't draw this in the exam, it's just to illustrate to you guys that I've got like a test tube with some plant tissue in there, and when it's 0.0 calcium ions in this solution, there's 0 uptake. When there's 0.1, there's 0 uptake, as it's showing on my graph up here. But when it gets to 0.2, I do get uptake. Right, so 0.1, because when it gets above 0.1, it starts to move into the tissue. Right, so that's what, this tissue must have 0.1 calcium ion concentration in it. So now I'm just writing true facts. So I'm saying that, yeah, the ions enter by facilitated diffusion from 0.1 to 0.3 milligrams per decimeter cubed. So I'm saying, yeah, from here to here, it's coming in by facilitated diffusion. I then put plant tissue as a calcium ion concentration of 0.1. So active transport is used at concentrations less than 0.1. So when it's here, in this bit of the graph, let's just get my highlighter again. So up to kind of like there in the graph, it's doing active transport. So that is just up to kind of like that point there. Get rid of that. Undo my draw. Oh, there you go. Yeah, so it's doing active transport, and I know that because of the comparison between the two curves. Again, hard question is this. I've then put, let me just zoom in a bit, my answers. Point areas. Yeah, so again, it's getting this 0.1. Once you get that idea, then it's actually not a bad question. Well, it's not as hard as it makes out. It's kind of understanding what the graph's showing. I'm then just going to write some facts. That oxygen is needed for aerobic respiration because because ATP is needed for active transport. So in effect, I have to say that active transport requires ATP, and that's made in aerobic respiration when oxygen is present. Plant cells actually transport calcium ions up its concentration gradient. Yeah, so when I'm in concentrations less than 0.1 milligrams per decimeter cubed, at that first bit of the graph, oxygen, so ATP, is not required for facilitated diffusion. Rate becomes limited by the number of available transport proteins. So I can also talk about that, the fact that the curve here is starting to curve over. I've reached the bit where I'm reaching a maximum rate. If I went to 0.4 molar, I'd get no further increase. All the transport proteins would be saturated in the cell membrane. Hard question that. If you're picking up like 3 marks on that, well done. However, you should be getting like 5 marks on this because this is book work. This is just learning co-transport. Cells lining the ileum absorb monosaccharide glucose by co-transport. Explain how. So yeah, sodium ions are actively transported out of the cells using energy from respiration or using ATP. A bit about active transport, how it does it, that proteins change shape to do that. The result of that is that the cell's now got a low concentration of sodium ions in the cell. Therefore, sodium ions can diffuse into the cell by facilitated diffusion. Again, big word. How many on this homework? If you facilitated diffusion used correctly gets 3 marks, and most people didn't mention facilitated diffusion. And that's down its concentration gradient. So again, just saying what facilitated diffusion is, causing glucose to be pulled into the cell with it. I could have put via a protein, but I've used my protein already. Mark up there. But yeah, 5 marks. How many marks? 1, 2, 3, 4, 5, 6, 7. Where's again 5 marks? How is diffusion and osmosis similar? Well, they're both passive processes or work with kinetic energy or don't require energy from respiration, and both move stuff down a concentration gradient. And then we get to nearly our last question. So using your knowledge of transport across membranes to explain the shape of the curve in the graph for uptake of monosaccharides, well, that's glucose, it's just told us previously. And, sorry. I shall shut up there as I'm trying to do 2 things at once. Right, I'm back on it. So between A and B, how's it moving in there? Well, it's just moving in. To explain the shape of the curve, it's going up because it's limited by the external concentration. As I increase the concentration outside of glucose, more goes in. So it's limited by the external concentration. As the external concentration increases, so does the rate of entry. And between C and D, all right, it's gone flat now, horizontal. That means the rate of entry is limited due to the number of available transport proteins. How often have we seen that? Look how I've highlighted the word rate as well as I've gone through it. And then the graph, shimmy up slightly. The graph is evidence for monosaccharides being lipid-soluble molecules. Suggest how? Well, that's because the rate of entry is proportional to the external concentration. or it doesn't become limited. It's just going up. As I increase it, it goes up. More equals more, more equals more. And that's because monoglycerides can use any part of the phospholipid bilayer of the cell membrane to move across. So I've got this enormous cell membrane, enormous in relation to the size of a monoglyceride. So there's my cell membrane. There's a monoglyceride, that red dot. I've got proteins in the membrane. My green dot is glucose. Glucose has to use a blue dot to get into the cell, so my green dot has to go via that way. However, my red dot can go anywhere it wants. Yeah, just bump into the cell and it's in, hence why it's not limited. Whereas the green dot, the glucose is. So yeah, my red dot is monoglycerides, it's lipid soluble, meaning it can just cross any part of the phospholipid part of the cell membrane. And look how I've said both, phospholipid and cell membrane. The phospholipid part of the cell membrane, remember they are different things. And then last one, drawing the arrows in. Well, osmosis is the diffusion of water to the most negative water potential. Well, minus 134.9 is less than 134.7, as in negative. So yes, I've got my arrow going from left to right, and minus 133.2 is higher than minus 134.9, and therefore it comes in from the side. What I can't do is that. It can't do that because it needs to have a cell membrane joining it together. Hopefully that was useful. I found it fun. 12 minutes.